Well, in this last presentation of the introduction to the boundary scan architecture, we will look into the operation of the finite state machine that is called the test access port controller. This is a very important block because it controls the operation of all the test logic blocks. So after watching this presentation, you should be able to explain how the sequence of ones and zeros driven to the test mode select pin is able to control the operation of the on-chip boundary scan architecture. We will assume that we start from the test logic reset state, which is what happens when we power up the board. And when we are in the test logic reset state, all the boundary scan cells will be in transparent mode. That is to say, all the pins will be connected to the core circuitry, both at the inputs and outputs. You may recall that what we have to do to start with is to drive an appropriate sequence of ones and zeros to TMS, so that we set this multiplexer down in such a way that we are able to shift in the first instruction. So to shift in an instruction, we actually need to go to the finite state machine that is called a state that is called shift instruction register. So to go from test logic reset into shift instruction register, we need to start by driving a 0 to TMS and driving one clock pulse at TCK. So by setting TMS to 0 and driving one clock pulse at TCK, we go from test logic reset to run test idle. Well, nothing has yet happened to the operating mode of the boundary scan cells, of course, because we haven't yet shifted in any other instruction. But by driving now a 1 at TMS, we go to select data register scan, then another one takes us to select instruction register scan, and now notice that by driving a 0 to TMS, we will go into a state called capture instruction register. And this is actually the moment when all the instruction registers in the boundary scan devices in the board will capture that fixed pattern comprising 0, 1 in the two last bits. So this is the fixed pattern that when it is shifted out enables us to check the integrity of the boundary scan board itself, the boundary scan chain itself. Then by driving a 0 to TMS, we go from capture instruction register into shift instruction register. And this is the moment when the multiplexer is set to our required operating mode. And while we remain in shift instruction register, that is to say, while we keep TMS at 0, we will be shifting in bits, zeros and ones, into the instruction register. We will have to stay in this state for as many clock cycles as needed to shift in all the bits to the instruction register. If we have an 8-bit instruction register, for example, then we must stay here for 7 clock cycles, because on clock cycle number 8, the last one, we must move out from shift into exit instruction register states. And the reason is that if we stay there for all the clock cycles, then on the next clock cycle we would still shift something. So we will stay in the shift state for a number of clock cycles, which is equal to the number of bits in the instruction register minus 1, because the last clock cycle will also be used to go out of the shift state. Well, then we will go from exit instruction register to update instruction register by driving a 1 at TMS. And this is the moment when the new instruction becomes valid. So if you look at the operating mode of the boundary scan cell, when we go from exit to update, you will see that the boundary scan cells now reverted to test mode. That is to say, all the pins are now isolated from the core circuitry. And this happened when we made the new instruction valid, assuming, of course, that this was the external test instruction. We are now able to send in test vectors to the boundary scan register, and in order to do so we have to go into the so-called shift data register state. Notice that the states for the data registers are similar to the states for the instruction register. So we have to drive, in this case the easiest way will be to drive a 1 and then a 0 and another 0 and we have gone into the shift data register state. Now notice that while going through the capture data register state, the input multiplexer in the cells was connected to its upper input, and this means that all the capture shift stages in the cells, in the boundary scan cells, have captured what was present at their inputs. And this happens when we go through the capture data register state. Now, while going from capture data register into shift, then the input multiplexer will change state, as you have seen here. And now, while we are in the shift data register state, we have this scan path comprising all the boundary scan cells, because all the input multiplexers are connected to the shift mode, setting up this serial path. Again, we will be here for a number of clock cycles, which is equal to the number of boundary scan cells minus 1, since in the very last clock cycle we will have to go out from shift into exit. Well, when this happens, we have shifted into the boundary scan register the required test pattern, but we have not yet updated the outputs. That is to say, each capture shift stage will now hold the new value, but it has not yet been transferred to the latch stage. And as you may have guessed, this will happen when we go from exit into update. So when we go from exit to update data register, the content of the capture shift stage is uploaded to the latch stage, and the new test vector comes out to the output pins. And then we just have to repeat this sequence, going from update into capture to capture the test responses, and then from capture to shift, so that we shift out the test responses and shift in the new test vectors. Thanks for your attention.